formulas right here with our basic parabola with the vertical axis, the one that you usually see with the vertex being at 0, 0. And the parabola opens upwards, as well as with the y squared equals 4px, where the graph opens downwards. And in higher level calculus, you will go into three-dimensional parabolas, and I am not at that level yet. One day I will be. And the standard form for parabolas as well as y equals ax squared plus bx plus c. All right, so focus. The focus is where all the energy converges inside the parabola. From the focus point to the point on a curve, and perpendicularly from the directrix to that point, it should be equal distance, which is 2p from focus to directrix. And the two distances will always be the same ratio. If they are not, it's not a parabola, because they are not equal distance from the focus. Finding the focus in architecture. One of the many applications is architecture and structure building. And here I have the Hume Bridge, which is in Manchester, England. And I went ahead and just found out the statistics for it, or the stats for it. The height is 82 feet, its length is 171 feet, and through the formula y equals ax squared, I'm able to figure out its vertex, its and its focus, and the directrix along with that. So with the formula I used, I was able to split 171 into 85.5, negative and positive, because I went ahead and put the parabola on with the vertex being at 0, 82 feet. Which is right here, 0, 82 feet. And through that, I had points at x-intercepts, 2x-intercepts, negative 85.5 and positive 85.5. And through this, I was able to calculate p, which is 23, and that's 23 from the vertex, which is the highest point, the maximum point, which is 82. Subtracting those two, I get the point of the focus is at 59 inside the structure. Finding the equation, as well as using the focus and vertex to calculate the directrix. Well, the directrix is just pretty much negative p, and p is calculated to be 59. So the directrix will be y equals 59, or y equals 105. And this right here is how you would formulate the equation into the general form. So that we can say that p equals 59, so the directrix equals, I put y equals negative 59, but it should be 105, leading to the equation of the parabola x squared equals 459y, or x squared equals 236y. Here's another example finding the focus with the equation, given the equation y equals negative x squared. And you write in standard form, go ahead and get the y equal to negative y and x squared, and in parentheses, if you recall, x squared is equal to 4py. We go ahead and substitute 4py into negative y and translate it, so we take away the y, divide negative y by y, and we get 4p equals 1, negative 1. And then the p is equal to negative 1/4. Now with the directrix, which will be y equals negative p up here, you have to take into consideration that p is already negative. So when you finally do the directrix, it will be a positive number, which will put you on the positive y-axis, and it will be 1/4, which is the directrix here. The reason parabolas, they have a special property of law of reflection, which gives it that ability to have the focus in its position, which is when the energy arrives inside the parabola, it tends to converge at this point, known as the focus. And the way it works is you have the ray of incident hitting the surface, and it's tangent to the parabola, and then the ray of and the angle of reflection is exactly the opposite of that. And this would be the angle of reflection off the normal line, which is tangent to the parabola. Well, why does this matter, you might be thinking? Math, usually you don't hear a lot about applications in your classes. Teachers don't usually give too many applications, or the coursework material doesn't allow time for it. But security, the military, again, they made early radar detection because of parabolas and understanding parabolic microphones and reflectors. Safety in headlights, without that we wouldn't be able to get those high beam headlights and provide safety on the highways and roads. Entertainment, satellite dishes provide cable. They give you Angry Bird apps, which they use the laws of projectile motion. Support in bridges, architecture, everywhere you go you see a bridge over suspended water. They use a parabolic suspension system to hold it in place. and energy with the solar power. Focusing it into one spot collects all the energy and collects all the energy. Okay, so my next part was the design process. I first had to figure out what the problem was, and the problem was locating the focus at whatever parabolic structure I chose and a convenient source of materials for the structure. First, I defined my work criteria and goals, and this is a list of what I thought might be relevant to the research that I felt would impact the final product. Questions such as, will it be collapsible? Will I be able to close the umbrella or be able to move it easy into my pocket or such? Will it tune out the ambient sound in the back, the feedback? How will it look? Will I be able to hear from far away? And will it be recyclable and reliable? Questions like that really helped me pinpoint my final product. My goal was to construct a parabolic reflector microphone that was economic, took away the feedback, and was made up of household materials or recyclable, so it was inexpensive. The research and gathering that I did was over a lot of extensive research. I went to Yahoo, did many searches, and came up with ways to build your own parabolic reflector microphone, as well as using the mathematics formula to figure out the theoretical position for the focus, as well as experimental location for the focus. These are just the figures that I used, the images. I took a screenshot of my research and I was able to figure out how it would look, and over here is an umbrella design, as well as a few other designs that I felt were a little more expensive to create, so I did with what I could. Then I thought of ways to make it better if I could innovate the product in the end. And these ideas right here were just like brainstorming. Maybe I could use a salad bowl, maybe I could use a hat or helmet, and then some other ideas were like the shape of an eyeball as well. Just brainstorming, I decided to put it down. And then I thought of creative ways to innovate. Aluminum foil is one way to make the synthetic material more reflective, as well as the umbrella is easy household material. And for the microphone, I was debating over whether using Bluetooth headphone headsets that have a mic capability, or even a karaoke machine you might have at the house, which most people, well, me, has a karaoke machine at the house. I decided to go ahead and label my work criteria and give it a weight, so that way when I'm actually figuring out the products, I can pick the best choice based off of this criteria that I have. And I decided to go ahead and give recyclable and cost the biggest factor in creating my structure, because that was the most important factor for me. These are a few of the solutions I had. I'm just going to go through a few of them. One problem was the handle and how much support it could hold and whether it'd be strong or reliable. I came to the final conclusion that a hanger would be the best choice because it's easily accessible. I have a bunch of them at home. And the other one was the structure of the parabola itself, whether to use a salad bowl, a helmet, an umbrella, or even a satellite dish. And these right here are the pros and cons to each one individually. This is a video of me developing the first one and showing how it is, but it is 3 minutes long, so I will have to skip it due to time limits. This right here is one of my other prototypes, which actually turned out to be my final one. The reason I put some of the foil on some of it is because of the appearance. I wanted to make sure it was a factor still in the final product. And the reflective material, as well as adding an air pump onto the hanger to provide more stability and more of a grip for your hand. And I added a mount, that way you could easily hands-free use one hand, point, and shoot. This right here is a test over the first one, which is just the microphone on its own. So this is just the audio playing with the microphone listening to it. And then this will be with the umbrella. As you can hear, it has a higher quality sound to it. The one issue with this was I had to be fairly close to the source of sound, which of course was okay because in the end, the focus actually showed a lot more improvement. So my decision was finally choosing the products, and I went ahead and the red is what I actually chose, and I graded it, made a 92, and that's why I chose it, because I had the higher grading off my working criteria. These are some of the tools I used, glue gun, hammer, scissors, safety goggles. These are some other materials I had used, the karaoke machine, air pump, and I took all those apart and designed my parabolic reflector microphone. This is the procedures I have listed. I also have it in my formal report of how I actually designed it and put it all together. Some of the issues I had were the close hanger was really narrow and it really swiveled a lot in your hand. So I was able to figure out an air pump would best be the solution for it. These are my references, and my name's Armando Cruz, and my email is up here if we have any other questions. Thank you for listening.
Are you going to demonstrate?
Oh, I can, yes. The only thing is the the speakers on my phone aren't as loud as the audio clip I have on there. Oh. And the reason I chose a cell phone dial tone is because it had a consistent sound. I tried music and lyrics, but with that, the problem was the pitch of the person's voice changes as they sing. Now we'll be doing the same tone. And then with this, you just open up your voice recording app, start it. And although it is very basic right now, my design process led me to this. And right here, once you have it recorded, it saves onto your cell phone or device that you use. You go ahead and take out the earbuds, which allows it to go out, and you play it right off. And just like that, you're able to point, record, and document the source of sound.
I don't think we have much time for questions, but I would like to ask one, because you introduced the problem with your spy microphone. And so how far away, first of all, could you pick up sounds with the one that you built? And do you think that it could work for actually spying on conversations at a distance?
It did pick up sound, but the thing, from the distance I had measured, was about to the wall actually, and the sound was very faint, too faint for me to actually want to use as part of my research or part of my developing and testing. So I went ahead and just went closer, that way you could actually hear the change in sound and quality of the microphone picking it up. But I hope to one day modify it, innovate it more with another design process based off of this one, to really remodify and innovate it to pick up greater sound from farther distances.
Does anyone else have any questions?
Well, thank you for your time and for listening.
Thank you.